Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to be talking about function transformations and operations. So these are the three transformations we're going to be looking at. We have the translation, a vertical slide or a horizontal slide, the dilation, a vertical or horizontal stretch, and then a reflection, a vertical or horizontal flip. For all of these, we're going to be taking some function, and then we're going to be using a constant term where we'll either be adding or subtracting, multiplying or dividing, and then for the reflection, we're simply going to be applying a negative to it. Now, a really good guide, and a thing I hope you'll notice, is that if we do the operation outside the function, then it's going to be a vertical change. If we do the operation inside the function, it's going to be a horizontal change. And when you think about the definition we're using for a function, that is, it's a rule that assigns from the range an element to each element in the domain, then that should make sense, because when we do something outside the function, we're affecting the elements in the range. And we do something inside the function, we're affecting the elements in the domain. Okay? So let's go ahead and take a look at these in Desmos. Welcome to Desmos. If you've never seen this before, this is an online graphing calculator that you can use to replace pretty much any graphing calculator that you might be carrying around. You can also get this as a free app on iPhones or Android devices. Also, I would highly suggest you get used to Desmos as a graphing calculator because it's very similar to what College Board uses on the SAT and all of their other online tests. Now, we're going to be looking at various functions, and I have one loaded up here, and we're just going to go ahead and look at what happens when we apply transformations to them. So we have a function, and we have transformations we're going to use. Now, just a quick reminder, I'm going to go ahead and write them on the screen here. So I'm just going to demonstrate what happens with each of these really quickly, and then I'm going to give you a moment to think about exactly what the effect would be on the graph based on the table. Okay? So let's go and take a look real fast at these guys. So to do this, we're going to go ahead and use some of the cooler functions of Desmos here, and we're going to go f of x, and we're going to say plus c. We're going to sit here and we're going to add our slider, and we're going to go ahead and use 3. Okay? Now, what you can see here is that we have put a new function in here in black. So our original function is in blue, and our new function is in black. And so because we added our constant outside the function, it did exactly what we expected. It shifted up, translated up. So if we are now to change this to a minus, it would translate down. Let's go ahead and do that, exactly as expected. If we were to move this C into the parentheses, it's going to shift left and right. And what I want you to notice here is that it's going to move opposite. And the reason it does this is because we want to produce a function that has the same output as our original function. But because we're going to be in this, the first thing we're going to do is add our constant. That means we're going to be using, or we're going to be inputting larger domain. So we have to choose smaller domain or smaller inputs in order to produce those same outputs, which effectively is going to shift us to the left. Watch. See? So we've shifted left instead of right, which would be normally what happens when you add. So we've shifted the graph into the negative. And again, that's because we need to use smaller domain values to produce the same range outputs. Okay? Now, then we go here and we say a negative, and as you can see, we shifted to the right. Now, if we multiply by that c, we've gotten bigger, and if we were to go look at these values, you'd see that we got bigger by a factor of 3. And this is multiplicative, so you'll notice that where our y value is 0, we didn't change. So these points stayed the same because we're multiplying by that constant term. And only the y values changed. We're going to look at that in a table in a moment. And then if we were to go 1 divided by c, boop, you'll see that we shrunk in that way. Now, when we go to the inside, just like how on the translation, it worked opposite. Instead of shifting to the right with addition, we shifted left. This is going to do a shrink and a stretch, the dilation, and it's going to be inverted. So when we multiply, we're going to get in the horizontal, instead of getting a horizontal stretch, we're going to get a horizontal shrink. Okay? So watch. When we multiplied by our constant, we got a vertical stretch by a factor of 3. So when we multiply inside, we're going to get a horizontal shrink by a factor of 3. Bam. See? Notice we are the same height, but we have shrunk in by a factor of 3. And then if we were to go with the division, boop, we get the stretch by the factor of 3. Again, horizontally. Okay? Maintaining exactly what we said. And then, of course, let's do our negatives. If we do the negative outside, we're going to flip. Now, or vertically, when we flip vertically, it's a flip across the x-axis. So it's a little bit weird because we do the negative outside, which means normally we'd say we're doing this in the horizontal, but when we say it, we say we flip about the x. But that's because it's just weird how we talk about it. So again, a horizontal flip is about the y, or about the x-axis. And then if we do it to the inside, you'll see that we flip about the y-axis, a horizontal flip. And there you go. Okay? Now, here's the part I want you to think about. We're going to use a different function here. So I'm going to load up a function here. And let's load up h of x. Okay, nice little function here, nice parabola. Okay, and let's bring up a table. And let's select some x values that are all defined, because you notice that we aren't in the negative over here. Our function isn't over here. So let's go with some values where we are defined here. We're going to go with 1, 2, 5. Let's go with 1, 2, 3, 4, and 5. Those should be nice values. So 1, 2, 3, 4, and 5. Okay. So we have some nice friendly values here, 1, 2, 3, 4, and 5. What I want you to think about is how are these values going to change when we perform the following transformations. Okay? So take the following transformations and see how this function, this table would change. So I've hid the graph in the table, and here's what I'd like you to do. Go ahead and try to figure out what the new values would be for the points that were in the table given these transformations. And if you want an extra challenge, go ahead and before you put the new transformations into Desmos, try to graph the functions by hand. Just sketch it out based on these points and what you know should happen to those points based on the transformations. I'm going to show those graphs and tables in 3, 2, 1. So here we have our h of x, and then here's our r of x. As you can see, it moved up by 3, and here are those corresponding points. Each of the y values, we simply added 3 to. Here's our s of x, and we expected it to move to the right by 2, and sure enough it did, and so each of our x values, the domain, had to move to the right by 2. If we go down to the t, that one, we stretched vertically by 3 by a factor of 3, so each of our y values multiplied by a factor of 3. Okay, you have to scooch up so you can see it, but as you can see, it got very tall and skinny. Okay, and then for our last one, we did a reflection across the y. It was a horizontal reflection, so each of our x values got a negative applied to it, and we had a reflection across the y. And that's going to be it for our review of transformations. Next, we're going to look at operations. Okay, so the last thing we're going to talk about here are the function operations, and they're obviously broken up into two pieces. The top are the basic operations that are just like the ones we use in arithmetic. And we're not going to talk a whole lot about those because they work just like they do in arithmetic, and there's not a whole lot to say there other than this part in the bottom where you have to consider the domain of the resulting function. That's not very difficult though for these because all you have to do is take the intersection of the domain of the functions that you are performing the operation on. That also means, however, that you can only perform the operation if there is an overlap in the domain, because the operation is only defined where the functions themselves are defined simultaneously, okay? So an example here would be that if I have the domain of f of x defined on negative infinity and 3, and my domain of g of x is defined on 0 and positive infinity, then my resulting domain would be 0 to 3. That also means I can only perform whatever my given operation is on 0 to 3. The other thing to think about is that if that operation was division, I have to worry about the fact that I can't have 0 in the denominator, so I would have to add the additional caveat that my domain would be 0 to 3 given that g of x is not equal to 0, just like we do with rational functions. Now, the more interesting operation is composition. Composition is when we take one function and we stuff it into another function. And we're only working with two functions here, but you can actually do this with any number of functions, provided that just like with the other operations, the functions that you are composing are defined on each other's domain. Specifically, that the function you are putting into the other function is defined on that function's domain. Meaning, it's kind of weird to say this, the most inside function has to be defined on the outer function's domain, and then that function would have to be defined on the next outer function's domain, and so on and so forth, okay? Going out, okay? And then when we're talking about the domain of the resulting function, it's not quite as simple as the above situation. Because when we're talking about composing the functions, you have to worry about the domain of the inside function and then the domain of the entire composed function, because things can get a little bit messy when we're talking about composing functions, because you might be working with some rather tricky situations, such as stuffing a logarithm into a trigonometric function, or sticking a fifth degree polynomial into an exponential function. All kinds of weird things can happen, and stuff gets a little nutty. However, that also is where things get really interesting in calculus, and we have some really cool special rules that we use for dealing with those things, which is also why we want to make sure that we review composition of functions. Another thing that's really important about composition of functions is that you can take what looks to be a very complicated function and actually decompose it into multiple functions, okay? So I've just given you an example here where we have two simple functions. Well, I say simple, but we have two functions, and they're simple because they've only got one variable here. So we can't really decompose those. And we're just going to go ahead and compose these functions exactly how I have it up here. We're going to take g of x and stick it into f of x, okay? And then we're going to look at what the domain of that function would be. And then once we're done doing this, I'm actually going to leave you with a couple of problems to try, and I'm going to leave the answers to those problems at the end of the outro. So let's go ahead and do this one, and then we'll be done. So to compose this, we're simply going to take this function, stick it in parentheses, and put it where the x is in our other function, okay? So to do that, we're going to say our f of x is 3, and then we take our g of x, put it here, So that's the root of x minus 5, parenthesis, and then we go cubed plus 4. Okay? And that's it. We're done. So that would be f of g of x. Okay. Now, if we look at our just plain f of x is defined on all reals. So we don't really need to worry about that. It's a polynomial. Polynomials are defined across from negative infinity to positive infinity. However, g of x does have a restriction. So that restriction is going to carry over into our composed function. And that restriction is we can't have a negative under our square root when we're working in the real numbers. And in this situation, unless we say otherwise, we're typically working in the real numbers. Usually if you're working with a complex plane, you declare it. So we're working in the real numbers. So that means our domain is limited. Our domain is limited from 5, because we can have 5. That would put it 0. The square root of 0 is fine. So our domain is limited at 5 up to infinity. And so that would be the domain of our composed function. Okay? Now, one thing I want you to think about, and do this on your own, how does it change if we reverse this? Is it the same? Is g of f exactly the same as f of g? Try it yourself. See if it is. See if they're equal. Okay? And then I'm going to go ahead and give you a couple of problems to try, and I'll show you the answers to those at the end of the outro. So I hope that review of function transformations and operations helped. And as promised, here are the answers to those exercises I left at the end of the operations section.